a pleasure to be here today and share with you some of my own passion at the intersection of a few different worlds. And let me just make sure we're live. Can everyone hear me okay? Okay. So I live on the intersection of many different worlds: physics, biology, and nanotechnology. And right at that intersection of those worlds is emerging a new interface, a new frontier, if you will. I like to call it Nanobiophysics, and that's where my organization, Nanobiosym, that I'll tell you about, is working. And we actually work on 3 different levels. Nanobiosym, one question here, could I see the slides here? So I don't have to point back. So Nanobiosym works on 3 different levels. There's a research institute that focuses on creating new science and technology at the convergence, where physics, biotechnology, and medicine meet, and creating new science, new technologies, new spin-off companies, and new ways of solving global problems in healthcare, energy, and the environment. And the idea is operating at that convergence point. And Nanobiosym Diagnostics is focused on a product platform we've developed out of this synergy called Gene Radar, which I'll tell you about. And we've also started something called a global initiative to help bring some of these emerging technologies into developing world countries around the world, with an idea of it's not enough to have game-changing technology platforms. How do you bring them into some of the most remote rural areas of the world? And I like to say create sort of a clash of civilizations. And so we'll talk a little bit about that. What you see here is actually rural Mississippi, the deep south of Gone with the Wind fame. This is where I grew up, and I got to spend a lot of time meditating in nature with chickens and peacocks in my backyard. And it was in these early years that I developed a kind of an inspiration that there has to be an underlying unity in nature. On one hand, I fell in love with physics and mathematics. On the other hand, my dad was a local town surgeon, so I would get to go to the operating room as a kid and scrub in and help operate on patients. Happy you're not one of those patients. Spending time in nature, and this is the rural south of the early 1970s, where black people and white people lived on different sides of the railroad. My parents had immigrated from India, and we were probably the only Indian ethnic family for miles around. And so you can see at a young age, I learned how to live at the intersection of many different worlds. And so, but amidst all this was this underlying desire that there has to, or this belief that there has to be an underlying unity in nature. And the same rules of math and physics that we use to understand the far reaches of the universe must apply to life and living systems, and medicine and biotechnology. And so that was kind of the quest. And however, the deeper I went in my study in physics as well as medicine, whether at Stanford and later Harvard and MIT, I just became more and more aware of the divide, how big that divide is in the modern scientific context between physics and medicine. Modern physics, as many of you know, was developed in the context mostly of inanimate matter, and hadn't really come to terms with life, living systems, things like consciousness, open, and living systems are fundamentally open, and most of our physics was developed around closed systems, where the interaction with the environment was treated as best as a perturbation. And modern medicine, on the other hand, was really is practiced at the level of chemistry and molecular biology. And very little was understood about how physics plays a role in physiological processes. Things like mechanical forces, electromagnetic fields, how are they coupled to molecular and cellular processes. So this kind of quest kind of inspired me and kind of haunted me in a way to say, there's got to be a way to bring these worlds together under a unified framework. And for me, nanotechnology became a bridge to help bring the worlds of physics and biology together in a more hardcore scientific way. And it was actually one of my childhood heroes. I was reading Einstein as you see here, who said to Leo Szilard later in his life, when he was exasperated looking at life and living systems, that one can best appreciate from a study of life and living things how primitive physics still is. So let me to start hypothesizing and thinking about, what does it take? What are we going to have to do to physics to be able to come to terms with life and living systems in a more hardcore scientific way, so that the two can really be brought together under a unifying framework? So about 100 years ago, Albert Einstein gave us a framework to understand matter and energy on some sort of equivalent footing. And it seems to me that in order for physics to come to adequate terms with living systems, things like life and consciousness, we're going to have to expand the framework of physics to be able to deal with open systems that exchange matter, energy, and information with their environment, and also extend our theoretical and mathematical machinery in physics to bring matter, energy, and even information, and perhaps, to use a bold word, the word consciousness, to understand that interplay of matter, energy, and information in a hardcore scientific way. It's going to take rigorous definitions and really pushing the frontier. This is sort of the Wild West of physics, if you will. But it's going to take some hardy souls to kind of jump in there and try to really make sense of that. So about 15 years ago, I fell in love with this thing. These are nanomachines that read and write information in DNA. And these are tiny little motors that are operating in your body that run up and down DNA. And they're little tiny Xerox machines. They're Xeroxing the information stored in DNA. And what inspired me about this is that these are machines that read DNA and they're influenced not just by the information encoded in the DNA, but information embedded in the environment. And the question really is, how is information in the environment controlling or affecting how these little nanomotors read the information in your DNA? What role does the environment play in regulating that process? For example, two different people, identical twins, could have the exact same genome, and one could develop cancer and the other may not. And it could be not because of the DNA that they have, but what role the environment played in affecting how that information stored in the DNA got expressed. And so what really inspired me is how can we understand this coupling between the environment and how this nanomachines read and write information in DNA, and what's the mathematical machinery we can use to start to describe and predict how the different knobs in the environment are controlling the way information is read out of DNA. And I spent some time at the Santa Fe Institute digging into open systems, network physics, and the Santa Fe Institute studies all kinds of networks, Al-Qaeda networks to economic networks to the stock market. And I really wanted to look at these biological networks and see, can we actually push or create a language, a model to start to understand how different knobs in the environment can couple into these nanomachines and affect the way they read DNA. And at the same time, there were tools becoming available from physics and this new field called nanotechnology that made it possible to take a molecule of DNA, stretch it out, and study in real time or visualize how these little nanomachines are reading and writing DNA. So this convergence of these experimental tools, theoretical machinery from math and physics, diving into sort of these living systems at the nanoscale helped to sort of bring these different worlds together in a tractable way for me. So for the past 15 years, I've been looking at really how do we harness these nanomachines, but how do we learn what are the knobs in the environment that can control these nanomotors? And that involved understanding the underlying principles, the design principles by which these machines operate, and then developing the ability to control these motors by understanding the knobs in the environment and learning how to tune them. And then also developing a conceptual mathematical framework that can then predict and go hand in hand with what the experiments show us at the single molecule level. And then being able to elucidate how the motor's dynamics changes as you change different knobs in the environment. So this leads to kind of new ways of looking at this as well as new applications. So one of the kind of new ways of thinking about this is that you can think of these nanomachines as information processing machines. They're processing information stored not only in the DNA but in their environment. And so there's some frontiers there which I won't have time to talk about, but such as thinking about these molecular machines as information processing machines and asking bold questions like, do they process information quantum mechanically? And if so, could they be future architects, be a sort of architecture for future quantum computing devices? I'll tell you about a more down-to-earth application that we've developed about harnessing these nanomachines for enabling high-precision read-write of DNA, and a commercial product that we've created called Gene Radar, which I'll tell you about. So this is just to give you a little feel about these nanomachines. So this shows here how we can actually precision control how these motors move along DNA by changing different knobs in the environment. Here we're changing the mechanical stress on the DNA. And you can see that on the x-axis, you increase the tension, mechanical stress on the DNA, you can actually tune down the speed at which this enzyme reads DNA. So at zero tension, the enzyme is happily humming away at around 100, 150 bases a second. As you increase the mechanical force, you actually start to tune down its speed. Around 35 piconewtons, the enzyme comes to a screeching halt. And if you pull harder, you actually cause the motor to reverse gears and start running backwards and unzipping DNA. And so this is an example of how we can use a knob in the environment, like a mechanical force, to precision control this nanomotor as it's crawling along the DNA, and also induce its natural error correction capabilities. And this is some more data from my lab where we actually, in high precision, can visualize the motor running forward and backwards and be able to control it on demand. So you can see here, I don't have a pointer, but the first one, the motor is Xeroxing the DNA, and in the other one, editing mode, we actually cause the motor to reverse gear and start running backwards and start editing the DNA. So if you take the bottom graph is if you take the derivative of that, you can see that the motor doesn't move like your car on cruise control on the highway, but actually moves like your car in the middle of with a lot of traffic lights in the middle of the city, stopping and starting in stochastic burst and gaps. So here's a little movie to give you a feel of how this works. So you can take a molecule of DNA, stretch it out, using techniques like optical magnetic manipulation. And you can see now this is an enzyme. This is the nanomotor. It's taking out building blocks from the environment and Xeroxing the DNA template. And that's the kind of graph we can generate by observing in real time the movement of this enzyme along the DNA. Now we increase the mechanical force. You can see we kind of slow down how the nanomachine is chomping along the DNA. Now we really pull hard, and we actually make it stop in its tracks. It can't move anymore, and it's just struggling. And if we pull really, really hard, we actually get the motor to run backwards. And so it's in reverse gear, running backwards. And what this really is an example of everything, the DNA, the enzyme, everything's the same. All we're doing is changing the environment. And by changing these knobs in the environment, we're affecting. And the real question this really opens up is what other information is embedded in the environment? And how is it talking to this enzyme as it's crawling along the DNA? And how can we bring sort of not only the experimental tools from physics, but our theoretical concepts to really probe deeply into understanding this coupling between the environment and these open biological systems? And so what are the applications to kind of shift gear that we can create once we can learn how to control these nanomachines? That's the other question that haunted me for many years. And so how do we take this platform, the ability to precision control nanomachines as they read and write DNA, and create a number of different applications that can impact many industries? So I'll tell you about Gene Radar, which is one that we've developed over the past few years, but some of the other ones that we're exploring in our incubator. One, for example, is ultra-efficient energy transduction. So it turns out that your car, driving along, gives you about 20 to 40% efficiency in converting oil from, say, the Middle East into mechanical work. These nanomotors can be 99.9% efficient in converting chemical energy in the form of ATP into mechanical work as they crawl along the DNA railroad track. And what we're doing is we're really controlling this energy conversion process by controlling these environmental knobs. And we're controlling this energy conversion process on very small scales. The ability to read and write DNA on very small scales. That has a number of applications, as wild as information storage, including in biomaterials and in DNA. I mentioned I won't get into sort of thinking about this as potential quantum computing systems. That's sort of a separate talk. But I will tell you a little bit about gene radar. Before I do that, I'll just give you another childhood hero. So Feynman, over 50 years ago, made a calculation that if we were to take all the world's information, all the libraries of Alexandria, today it would be all the Google websites, and pack all of that information into DNA, we could take all the world's information and get it into DNA, into a box whose thickness is less than that of a human hair. And this remarkable information packing density is possible because of the high ability of DNA to store information. And these nanomachines are the read-write machines of nature. This is by establishing the ability to control them, we can read and write information into DNA on demand. So envision in the future, instead of having your CD-ROMs and magnetic storage devices, you may have the ability to read and write information into molecules of DNA, and then these would be the nanomachines that we would control to go and access that information on demand and write it on demand. So those are some examples. So now a little more closer to where we are today. So the spin-off entity we've developed has developed a platform called Gene Radar, which is a nanochip technology where you can put a drop of blood or saliva into a chip, stick it into a portable device, and rapidly diagnose what kind of disease a person has. And envision like a cell phone-like device. Our aim with this is very modestly to revolutionize healthcare globally. We'd like to enable real-time point-of-care diagnosis by empowering patients to diagnose their own disease, taking the ability of diagnosing disease outside of a hospital or pathology lab, bringing it into the patient's bedside, doctors' offices, people's homes, and even rural remote villages in the developing world. And this is from a military briefing I did some years ago. This has to do with SARS. So, why did it take a group of multinational experts working 24 hours a day, 7 days a week, almost a month, to go from when the virus was first recognized by the World Health Organization to when it was first sequenced? What happened? There was no way of containing the spread of the disease at borders. Infections continued to grow and spread. Thousands of people died, billions of dollars of economic loss. And this was our system at its very best. It was really tested. It was an emergency rapid response effort by many nations collaborating. Still, at our very best, it still took us a month to go from sample to answer. And this is an anatomical breakdown of why it took us a month. You take infected throat cells from patients, you grow them up via cell culture. This is the traditional way it was done. And then you beat up the cells and squeeze out the DNA. In this case, it was RNA. That takes about 2 days. And then you take the string of DNA or RNA, you chop it up into little chunks, 400 to 500 bases each, because the current technologies are not accurate and precise enough to go after the whole genome at once. And you do something called shotgun sequencing. That takes only 4 to 5 hours. But then you spend 2 weeks trying to cleverly recreate the original 30,000 base pair virus. So that takes another 2 weeks, some fancy supercomputer technology and some sophisticated bioinformatics people. So it took about 28 days total, a trailer-sized facility at best. And so what we did is we came in and said, can we use nanotechnology to kind of re-engineer this process? And we had, and by improving the precision and accuracy and control over how we read and write DNA, can we improve and get rid of some of the bottlenecks in this? And so we were able to show how we can get rid of some of these bottlenecks and actually re-engineer this process so it can happen on a small chip and then be read in a portable device, so you don't have to have this whole infrastructure that's traditional in these kinds of diagnostic capabilities. So what we have created out of that is something called Gene Radar. Radar stands for Rapid, Accurate, Deployable, Adaptable, Robust Gene-Based Detection System. And enabling ultra-sensitive diagnosis down to the nanoscale. And one of the things the military wanted is the ability to be robust in extreme environments and the ability to work out in the field. So the next time there is a pandemic, a swine flu, an avian flu, or a bioterrorist attack, instead of happening what happened in the blue curve, which is SARS, you'd have something more like the red curve. You would be able to use this as a device to rapidly contain the spread of infectious disease. So what we're doing, though, is we're seeing that this is a platform that can now affect many different markets, many different industrial needs, for not only biodefense, but life sciences, clinical diagnosis, and even things like water testing, food and beverage testing, crop testing, and we've even developed a collaboration to bring it into biofuels, low-cost algae fuels, where you would use this to select which strains of algae to use to help increase the yield. For example, if you take algae and you starve them, they get fatter. And if they get fatter, they make more oil. So you can tune not only their genetics, but their environment to make them produce more oil at a lower cost. But I think perhaps one of the biggest opportunities for platforms like this is in the developing world. There are 6.6 billion people on Earth. Everybody gets infected at some point in their life. And if we can make the ability of diagnosing disease cheap enough and accessible enough, and so that people at the bottom of the pyramid can really can have access to this, we can create an overnight kind of paradigm shift in how healthcare is not only delivered but accessed. And we're really empowering people all over the world to be able to have that information, diagnose their own disease, and then take the next step to get the access to the therapies that are necessary. And you may ask, well, why the developing world and what's the impact? I think there's a good case study provided by what happened in the cell phone industry. We saw a paradigm shift in the telecom industry when communications and computing devices became portable. And once the cost reached a certain threshold, you saw things like, rickshawallas, beggars, and farmers all using cell phones in villages, in rural, remote villages. We think we can help create a similar paradigm shift in the coming years in healthcare by taking that ability of diagnosing disease outside of a hospital infrastructure or lab infrastructure and bringing it out into the field, a portable device, disposable chip, and so it can be used in clinics, households, doctors' offices, and even rural, remote villages. And the developing world countries would have to invest billions of dollars to create the infrastructure the same thing in the area of telecom. They would have had to invest billions to create the infrastructure to overcome the lack of landlines. And by adopting wireless technology, they were able to quantum leap or leapfrog over this lack of infrastructure for a few millions of dollars. And so we think similarly, these kinds of technologies for sort of portable diagnostic healthcare can enable this sort of quantum leap and leapfrogging effect in countries which do not yet have the infrastructure, running water, electricity, roads, trained medical personnel that can be easily deployed.